All right, meow. Happy Friday. It's snowing again. What a fun day. Hey, Jackie's in the house. What's going on? When are you planning to teach? Giddy up. All right. And you, where do you go? Olaf? Carlton. All right. Okay. So we're going to talk about the day 2 of 11.1. We've been working permutations and combinations here. Um, and we are going to get into it. We have a fundamental counting principle today, so a little add-in. Um, fundamental counting principle, you might be given a situation where you have to tally up the number of choices or options or combinations of something, and you're given several choices, like this yogurt situation. So in the yogurt situation, we have one flavor of yogurt to choose from. You get one fruit, and you can only take one, so that does make a difference. You can take one of each choice, and then one topping. One way to show or illustrate this would be with like a tree diagram. So if I made a tree diagram, I would have 3 choices of yogurt, right, like that. And that would be chocolate, vanilla, or strawberry. And then off of each one of those, you would have 4 choices of fruit. So now you can hopefully kind of see, oh, I got how many different possibilities here at the end of all of these little branches? 12, right? 4 threes is 12. And off of each one of those, now you'd have 2 options for topping. So now, this is getting kind of crusty, but 2, 1, 2, 1, 2, 1, 2. You'd have 1, 2, 3, 4, 5, 6, 7, 8. 8 choices off of each branch of 3 now. And so what you should hopefully end up seeing here is that we have 3 options for yogurt type. We have 4 options for fruit, and we have 2 options for topping. And if you count up all the ends of all of these branches, you're going to have 3 eighths, which is 24. And to get 24 from all these different choices, you can multiply them all together. So there's this multiplication principle or fundamental counting theorem or principle. Can't remember what it's called exactly. That tells you can multiply all those different choices together to get your total number of possibilities, right? This one's kind of a silly question. You're going to get a haircut. Do you want them to wash your hair? They have 6 different kinds of shampoo and 4 different kinds of conditioners. How many different ways could they wash your hair? 6 times 4, which is 24. All right. Let's bring the energy today.
Woo! Yes!
Nice job. Okay. Here's just some different examples where you could use this fundamental counting principle. I'll let you do this one here. All right, so they came up with an answer, and it was 5 times 3 times 2, right? So 30 different Sammys. 30 different Sams. Makes sense. 5 choices of meat. Now we're only taking 1 choice, so that does make a difference. If you did, or if you're able to select 2, then that would be different. You'd have to use like our combination tool to say, oh, I want to take 2 different meats. Well, if it was 2 different meats, then it would be like, all right, well, I'm going to take 5, choose 2 different meats times. What if it was like 3 different types of bread? There's choices, but maybe you could pick 2 different, one on the top and one on the bottom slice. I mean, it gets to be a little silly, but it could be more complicated than just taking the number times the number times the number. And that's what gets to be tricky in this chapter, is how to know what to do. But these ones are pretty straightforward. How many identification codes can be made if you had 3 digits and 2 letters? Okay, so the product of all of those different possibilities, how many different ways can I have a digit? And it doesn't say you can't repeat. So how many different digits are there? 10? Like a number? Yep. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you could also have 10 for the other one, 10 for the other one. Okay, so all these 10 possibilities. And you really can't use like permutation for this because you could select the same digit twice. So you couldn't say like 10 permutate 3 because that would be like saying, okay, well, I can't use the same one twice if I'm going to do a permutation. So multiplication principle comes in sometimes for, just depends on the situation. How many letters in the alphabet? 26. So multiply all those together and you end up with like, I think it's 676,000 if I remember correctly. Any verification on that? No? All right. I'm sure someone will leave a comment in the comments if I'm wrong. Okay. How many different codes can be made with 2 digits and 2 letters? No repetition. So there might be some stipulations on that. So you have to use your thinking. You have to think about it. How many choices for the first digit? 10. Now the second digit would only have 9 options because you already used one and you can't use it twice. Same thing with letters, 26 and 25. So whatever the product of all those are. Thank you. Second one is 58,500. So that's quite a bit of possibility. Do you ever think about, like, you know how a locker combination, right? Yep, some of you guys don't really use your locker, but locker combos have, I think, like 50 digits. So there's like 0 through 49 maybe or something. So that would be how many possible locker combos? 50 times 50 times 50, which would be 125 times what? 1,000? Is that right, Jackie? 125,000? No. 50 times 50, that seems like low, doesn't it? But if you take 5 times 5 times 5, you get 125. And if you take 10 times 10 times 10, you get 1,000. So I kind of think it's right. So 125,000, unless I'm wrong. So think about that. Do you ever walk around the hall and go, wonder if I'm feeling lucky today? I'm going to see if I can guess this combo. Maybe I'm 1 in 125,000 lucky right now. I'm going to guess this combo. And you go up to the locker and it works. And you're like, oh, you'll never believe what happened to me. I totally guessed this locker combo. 1 in 125,000. No? You wouldn't do that? You did that one. See? Great. I knew someone would have done it. Nice job. Do that today. When you're going home, just stop at a random locker and see if you're 101 in 125,000 lucky. Just tell them it's an experiment for math. I'll get you out. I'll get you out of it. All right, here we go. Yesterday we talked about the two counting tools, permutation rule and the combination rule. And the only difference, the main difference, is that in combinations, order does not matter. And so since order doesn't matter, we divide out all the ways you can arrange however many things you're taking from the group. So if we're taking R things, R out of N things, we're taking R of them, I want to divide by R factorial because that will undo all the ways you can arrange those R things. So we talked about those yesterday and how to calculate and using the calculator to be able to make those calculations. Student asked, do we need to be able to know how to do like the rule, like 8 factorial over 8 minus 6 factorial, something like that? I think that was the question, right? And so I'm not going to make you do the rule or memorize the rule, but I want you to be able to understand kind of where it comes from, and then using the button on the calculator. So again, we talked about this as 8 times 7 times 6 times 5 times 4 times 3 times 2 factorial over, and then now this is, of course, 8 minus 6, or 2 factorial. So then this part ends up canceling out with that part. And so really this is a question of like how many different ways can you arrange 6 out of 8 things in order matters. And so that was, if we didn't want to use the rule and it just said, hey, I got 8 somethings, how many ways can I pick 6 of them in order matters? Then you would just go 1, 2, 3, 4, 5, 6, and you'd say, how many options do I have for the first one? 8 times the second one, 7 times 6 times 5 times 4 times 3. And that's what we end up doing when you're using that formula anyways. So you don't really have to use the formula. It's just kind of a shortcut, right? You could just use the multiplication principle with all of your different options, just like we have right here. But sometimes it becomes kind of annoying to have to type all that stuff in the calculator. And so we have a button for it. And it's also cleaner when we're doing like more complicated probabilities to just write, okay, how many ways can I pick like an ace out of a deck of cards, right? Like maybe you have a 5-card hand and you're like, all right, well, how many different ways can I have 3 aces out of the deck of cards? Well, you can have 3 aces, 4 choose 3 ways because there's 3 aces in the deck, right? So we start representing different like possibilities by using this notation. Or it's like, how many hearts are in a deck of cards? People don't really know cards anymore. They don't play a lot of cards. Some people do. There's 13 of each suit, so there's 13 hearts. So how many ways could you have a flush of hearts? How many different flushes of hearts are there? There's 5 cards in a hand if we're playing poker. And so that would be 13 hearts, and I'm going to choose 5 of them. Does the order matter? No, if you have a hand of cards, you have a hand of cards. It doesn't matter. Some people like to organize them from least to greatest in their hand. Some people don't really care. But so start representing stuff with those symbols. All right, so permutation order matters, combination it doesn't. Let's crank out some more examples of this. So let's see. Does order matter? Talent show. Top 3 performers of 15 will advance to the next round. I think it's just top 3, not first, second, and third, or not like gold, silver, and bronze or anything like that. So because of that, it is a combination. Order does not matter. So you would use 15 C3. I'm not gonna write them out. I'll just leave it in notation. But yeah, so you should know where the buttons are and how to use them. Okay. Basketball team, 12 members who can play any position. How many different ways can the coach put 5 people in the lineup? Since there's no positions, then there's no distinguishing between each player, and so you would have a combination of 12 take 5 at a time. I skipped a problem. Uh-oh. I didn't see it down there. Go back to number 7. Family of 5 plans to sit in the same row in a movie theater. This is a weird one. How many ways can the family be seated in 3 seats? Like, some people don't get to sit there or what? This is maybe what I should start doing. Put my 4-year-old in his own row. So I don't know, I kind of think order matters here. But I also can see where someone would think it doesn't matter because it's like, well, who gets to sit in that row? But I think sitting in that row, for me, order matters because, like, for me, I'm going to sit in the middle with the popcorn, and then the kids can grab the popcorn from the left and the right. I'm not going to sit on the end and have one kid climb over the other one to get popcorn and then have a fight in the theater. That's what I did last time. I gave them little cups, yeah. So anyway, I know this one could be argued both ways. I'm going to say permutation order matters because the way you're sitting in the row makes a difference, and that would be 5 permutate 3. Silly question there. Let's go to the next 2. Ingrid, stringing 3 different types of beads on a bracelet. How many? This one's also kind of. Oh, I skipped 9. I skip everything today. I just want to be done. It's Friday, I guess. Oh, this one's good. 4 people in a writing contest. A lot of competition. They're competing for first, second, and third prize. So there's basically just one loser who doesn't get a prize. How many ways can the 4 people be chosen? Since there's gold, silver, and bronze, it's going to be a permutation, right? Okay. Now off to Ingrid and her necklace bracelet making. I'd say she has 3 different types of beads. How many ways can she string the next 3 beads? I'm going to say order matters there. And so that's 3 permutate 3. Yeah.
So in this, it would be 3 explanation over 3 minus 3, and then you get a 0.
Yeah, so it's really 3 factorial. When you have 3 permutate all 3, it's the same as 3 factorial because it's 3 factorial over 3 minus 3 factorial, and 0 factorial is just 1. And so really, if you're taking all of them and permutating all of them, then it'd be just 3 factorial, which 3 times 2 times 1, you know? Yep. The 3 best essays in the contest. We just already did that one, didn't we? What the heck? What the heck? Did I skip any yet? Wait, 4 people in a writing contest. This is another writing contest? Jeez. Gold, silver, and bronze stars. There are 10 essays. Oh, gold, silver, and bronze means the order matters, so it's 10, 3. Okay. Is that it? Oh, okay. So basically it's order matters. Does order matter? Does order not matter? Sometimes it's tricky to decide. If you get it wrong, don't freak out. It's very common for students, or it's very common to get these things kind of mixed up at times. And that's why if you really want to make big decisions in life, it helps to involve more than one person's brain, right? So that's why we should always do group tests.
Yes.
All right. Happy Friday, under 20 minutes. Let's see where we stop at today. Multiple 10?